Okay, so today we're going to be talking about net change. Another way of saying net change is also net effects. Okay, usually it's called net change, and it's usually also called displacement. Yes, that word again. We have dealt with displacement before. In any case, displacement can be represented with the numerator of the difference quotient. And that's right before we started talking about derivatives, or using part of that to help us define the definition of a derivative. So we have seen it within that unit. So now it may be unusual to hear about displacement in our unit of integration right now. But displacement is actually the integral of v of t with respect to t from when t is equal to a to when t is equal to b. Okay? And a lot of times when you deal with these types of net change problem, displacement problems, you're given an initial value and you find out your displacement. Okay? And you noticed already probably that I added them together. Okay, so if let's say your original position was at 1, but your displacement is 2, you're not just going to say, okay, your position is 2. You started at 1, so it's probably something like 3. So this equals your new position. And like I said, a lot of questions deal with that, so try to keep that in mind. That this is important to kind of add them together to find your new position. Okay? Now, they could be talking about a position of an object, a body, a particle over some time t, from t to t plus delta t. So that actually would be delta t itself. So it kind of does tie in with that difference quotient that we're working with before. All right, so we have this example here, and we should probably get to it. So start copying it down. If you need to, pause the video to write it down into your notebooks. Do get this stuff as well that I've been writing. All right, so let's get to it. In our example, the velocity of a particle moving along a horizontal s-axis for 0 is less than or equal to t is less than or equal to 5 is, of course, ds over dt, but it is equal to t squared minus 8 over the quantity of t plus 1 squared. Now, looking at my notes, I realized that this wasn't actually said in the problem, but we're measuring along our horizontal s-axis in centimeters, and our time is measured in seconds. Okay, so I don't know what happened when I typed this out, but it just kind of disappeared, so I want to put it back in there. Okay, so in part A, it asks to describe the motion. So in the do now problems you had, you probably, or hopefully, started to write about having an initial velocity, whether it moves to the right or the positive direction or left in a negative direction, when it stops at t equals something seconds. So that's basically what we're going to do for part A here. Okay, so here we go. If I plug in 0 for t, this is going to give me my initial velocity. So I'm going to do that, and I find out I get -8 as an answer here. So we're going to say that the particle has, an abbreviated particle, an initial velocity of 8 seconds 8 centimeters per second. I got ahead of myself. And I didn't include the negative in this sentence because I'm going to say it moves to the left. You can also say towards the negative direction if you don't want to use the word left. So now we need to also find out where it's going. So this is very similar to when we did our first derivative test. So let's proceed. Take our derivative, set it equal to 0, and solve. And this one, you're going to need your graphing calculators. You will have your graphing calculators for this type of problem. And I know I'm going to end up using this as my answer, so I already rounded to 3 decimal places. Okay, but I want to check that it works. So you can either continue to check with your table, making sure that his critical point is indeed something that we can use. Okay, so it should be a sign change, and there is. And we also know that it goes from going to the left, then it switches to go from the right, and well, that should happen. So let's write a conclusion, or continue to write here. At t is approximately 1.255 seconds, the particle, I wrote that number better before, sorry about that, stops, it changes direction, and moves to the right. And our answer is going to move up here because I ran out of space. Moves to the right. Okay, there's one other thing we're going to say. So we started talking about an initial velocity. So we want to talk about its velocity at this point in time. So if we plug that in, we get approximately 24.77 centimeters per second. And we can do that by actually showing that part. But again, I kind of ran out of space, so we'll kind of squeeze it in here. Okay, so it goes to when t is 5, and I guess this is where I'm trying to plug it in here. So 5 squared minus 8 over the quantity 5 plus 1 squared is where I'm getting the 24.777. I just realized I missed that decimal. Please make sure you round to 3 decimal places. And we're done. That was a long part A, but hopefully, since you guys are working on the do now, this is something you should have been doing for that as well. So you may be thinking, well, what's really new here? So let's keep moving through the problem. Let me know if you have any questions. So part B. Before I start reading part B, if you need to pause the video to get down that last part, make sure that you do that. This should be in your notes. So part B says, suppose the initial position of the particle is s of 0 equals 9. What is the particle's position at t is equal to 1 second, or when t is equal to 5 seconds? So this is what I was talking about before, okay? So let's actually write this out in mathematical terms. So in part B, okay, we want to know the particle's position at t is equal to 1 second. So the displacement that we have here would be from 0 to 1. And v of t dt can be replaced with our expression of t squared minus 8 over the quantity of t plus 1 squared dt. So now if we take a look at this, we can integrate this by hand. I'm just going to have to rewrite that second part and use our properties of integrals. So if I rewrite it, I can pull out a -8. I already used u substitution. U is t plus 1, du is dt. So it's a nice substitution, or at least I think it's nice. So over here, we get to plug 1 and 0 into t cubed over 3. And over here, okay, we're going to end up getting a -1 in the denominator, making that a +8 on the outside. And this should be like a u to the negative first before I plug in 1 and 0 for t. So that's important that you know that we need to kind of transfer it back, okay? So I'm running out of a little bit of space here. So I'm going to go up here. 1 cubed over 3, 0 cubed over 3. We all know that's going to be 1/3. And we're adding the 8. That's a plus sign. And like I said, we're putting like the u back in there. So u was t plus 1, so that's going to be a negative first power. If you want to write it as a fraction, you don't have to. And we're plugging in 0, 1 now. So we get 1/3 and 8 times something. So if we plug in our 1, and we plug in our 0, okay, we get this to be -4. So 1/3 minus 4 becomes a -11/3. Okay, so for when t is equal to 1 minute, okay, we find that the particle moves 11/3 centimeters to the left, okay? So what's happening when it says that the initial position was 9 is that we need to add it. So we're not done yet. And I'm running out of space again. So we're going to add our initial position, where it starts, to the displacement. Okay? Keep the -11/3. So it started at 9, okay? But it moved 11 places to the 11/3 places to the left. So that makes it at 16/3 to be its position, or 5 1/3. And as I was saying, is missing from the typed part of this. This is measured in centimeters, so that's where this is. The axis is measured in centimeters. Okay? This is only actually part of part B. Okay? I apologize. This is only one part of part B. But now I think that you got the idea as to what we should do for part 2, okay, when it says when t is equal to 5 seconds, all right? So let's start erasing and putting in different expressions here. Okay, so we want to first find the displacement from where our particle starts at t is equal to 0 when t is equal to 5. So I'm erasing the 1 and I'm going to put 5 in. So we did a lot of this work before. You don't have to actually erase as I'm doing. What I would probably do is write this part right here. I'm going to circle it in green. That would be my first step. Now I actually also know what expressions I'm going to get when I'm integrating. So I don't need to show that work again. But I would write this down instead. Okay, I'm going to write this expression plus this one And notice I changed the upper limit of integration to when t is equal to 5. Okay, so I then am going to show the substitution. So I'm going to start circling in, I guess, blue. All right, so show the substitution of 5 instead of 1. And I'm going to circle this in blue. This would be my next step. And now, my last and final step. Okay. And this should be clear. It's at the top of your screen. Okay, we have 9 plus, okay. In this case, it actually turns out to be 35. Okay, so when t is equal to 5, okay, the particle moved to 44 centimeters, which is crazy, but cool. Okay, so once you get your displacement, okay, through our integration, and all those parts, add it to your initial position, and you get your answer for where the particle's position is at a different time, whether it be t equals 1, or in this case, when t is equal to 5 seconds. All right, let me know if you need any help with that, but hopefully for the first part in part B, you were able to follow, and for the second part of part B, you're able to figure out as to how to follow through that. C. So I'm giving you a moment just to kind of get yourself together in part B while I'm just reading part C, okay? In part C, it says, find the total distance traveled by the particle. So we're going to talk about finding total distance. We have discussed it before. Okay? I'm going to just keep talking. Velocity not only tells us how fast our particle is moving, I want to say, but also in what direction, which is why in the do now and again in this example, we're talking about, hey, it's moving to the left, or hey, it would be moving to the right. When it asks for total distance, okay, it does not matter about the left-right. They just want it in one direction, or like the movements in one direction. So that may be a little bit confusing, but if you remember that the total distance is the absolute value of the velocity function, then you're going to be like, oh yeah, that makes sense. Okay? Nothing new. You just have to remember for total distance, it's the absolute value of velocity. Okay. So hopefully you had some time to get down part B. So C, we want to integrate the absolute value of v of t with respect to t from when t is equal to 0 to t is equal to 5, because that's where it begins and starts. And this is the same as v of t. So please write that down so that you don't have to put it in the absolute value in our integral. And that's actually it. When you have to integrate with an absolute value, you are going to be using your graphing calculator. Okay? So when you plug this into your graphing calculator, you should get about 42.587, and you're going to write that in centimeters. And that is your total distance traveled from when t is equal to 0 to when t is equal to 5. And you're done. Okay? So it got simple to complex to simple again by the time we got back to part C. Let me know if you have any questions. Good luck on your practice. And Take it easy, one step at a time. Good luck.